Methane is a potent greenhouse gas. In the first 2 decades after a kilogram of methane is emitted into the atmosphere, it is about 80 times more effective than a similar amount of carbon dioxide at warming the Earth. Fortunately, the concentration of methane in the atmosphere is much lower than the concentration of carbon dioxide, and the mean residence time of methane molecules in the atmosphere is considerably shorter than that of carbon dioxide. The concentration of carbon dioxide in the atmosphere is approximately 200 times that of methane, so that fact, combined with the short mean residence time compared to carbon dioxide, results in methane's contribution to global warming being substantially lower than that of carbon dioxide. Estimates of methane's contribution vary, but generally range from about 16% to 28% of that of carbon dioxide. There are both natural and anthropogenic, that is, human-caused sources of methane in the atmosphere. The anthropogenic sources account for roughly half of all the methane that enters the atmosphere, but this contribution has been rising, though not at a steady rate, since the start of the Industrial Revolution. The anthropogenic contributors of atmospheric methane include livestock, which is estimated to contribute about 37%. The growing of rice is estimated to contribute about 15% of anthropogenic methane as well. The operation of landfills, wastewater treatment, and biomass burnings accounts for another roughly 20%. The remaining 28% or so of anthropogenic emissions come from the operations of the oil and gas industry. A recent review paper by Collins and others points out that the best opportunity to reduce the amount of methane entering the atmosphere can be found in the oil and gas industry. The reason for this is interesting. While methane leaks can occur anywhere in the oil and gas sector, including drilling and production, transportation, storage, and usage, by far the largest fraction of oil and gas industry methane that escapes into the atmosphere comes from a relatively small number of very large leaks, so-called super emitters. Generally, a leak emitting 30 kilograms per hour or more of methane is considered a super emitter. So by detecting and repairing these super emitters, a significant amount of methane can be kept out of the atmosphere. The picture on the left shows an example of one of these methane super emitters. The methane that's produced in the oil and gas industry that is prevented from entering the atmosphere directly eventually will get burned. When methane is burned, it produces carbon dioxide and water vapor, but the carbon dioxide released in the process causes much less global warming than the methane itself would have. The Collins paper points out that there are a variety of instruments and techniques that can be used to detect methane leaks. Ground-based instruments can detect extremely small leaks and can pinpoint the location of leaks to individual components in the production and delivery chain. In addition, ground-based instruments can operate on a 24-hour basis, so they can catch intermittent leaks. However, a ground-based detector is limited in the area it can cover, so it becomes very expensive to cover large areas with ground-based detection. Wider areas can be covered by instruments flown on aircraft, and these instruments are sensitive enough to detect leaks as small as 1 kilogram of methane per hour. However, instruments flown on aircraft might miss some intermittent leaks. Monitoring methane leaks from satellites provides the opportunity to get a global picture of the effectiveness that is being achieved in controlling the largest methane leaks. With currently available satellite-based methane detection devices, the detection limit is about 500 kilograms per hour, but improved satellite-based instruments might be able to push the limit down to 100 kilograms per hour. This would allow satellite methane monitors to identify 50 to 60% of major leaks. The Collins paper also identified another area where improved monitoring could reduce the amount of methane entering the atmosphere, namely determining how much methane is entering the atmosphere through the practice of flaring. While more and more oil industry operators are realizing that it is much more profitable to capture and sell the methane that comes from oil well drilling and operation, there remains many operating oil fields where the methane is simply burned off in these highly visible flares. In principle, burning the methane should convert it to carbon dioxide that has a lesser impact on climate change. However, many flare operations, like the one shown in this picture, don't provide complete combustion, so some methane from the flare enters the atmosphere. Improved methane monitoring would allow stricter controls on these flaring operations. Because the mean residence time of methane in the atmosphere is so much shorter than that of carbon dioxide, the effect of preventing more methane from entering the atmosphere has a rapid impact on the rise in global temperatures. The detection and repair of methane leaks from oil and gas operations provides the best opportunity to quickly reduce the amount of methane entering the atmosphere. The climate change payoff from improved methane leak detection will happen relatively quickly. Thus, it is critical to fund the development of improved methane monitoring techniques for use in ground-based, aircraft-based, and satellite-based leak detection efforts. Thanks for watching. I hope you have found this short video informative. Please view some of my other climate-related videos, and if you haven't already done so, please subscribe to my YouTube channel.